not like the idea?
Oh, Jim just pressed the record button, so we're good.
Okay. I'll ask you just one more time. Is anybody else uncomfortable having this recorded? All right, thanks.
Yeah, so it would be really awesome if by the end of reading this paper, if we could, you know, have all these things implemented in the idris-ct library. Yeah. Does anyone have questions about that library? I guess we can probably talk about that later. Yeah.
I would
Oh, sorry.
I would be interested to see something there, but yeah.
Okay. Yeah, I think maybe let's do that after we get through sort of some of the paper's questions, because I can see that going quite tangential.
Yeah.
So I have one question. I'm thinking when we look at the whole Idris as a language, can we point in some of these categories? Like.
Yep. I have a work in progress pull request right now that is moving towards proving that Idris is a Cartesian category.
Okay.
Yeah.
Cool.
And I can show some of that later. Okay. So then basic definitions of a category. I guess I have a question here. Is anyone seeing the definition of a category here for the first time?
It's only about the second or third time for me, so.
Okay, cool. Yeah. Isomorphisms for me, I think still get kind of tricky, and I have a question about that later. They tend to confuse me. Yeah, as I'm scrolling through this, I'm just hoping that anyone who had questions on that section of the paper will chime in. So we have categories and morphisms, associativity, examples of categories. Yeah?
It's interesting that they start right away with string diagrams. Normally you don't see that introduced in this way. Normally you see first categories and then here's how you can show them as string diagrams.
Yeah, that's why I felt a little bit comfortable with Feynman diagrams, because it seemed like they were using those. I don't know what a Feynman diagram is, but it seemed like they were using this notation, which is kind of close.
Yeah, it is really neat to see it that way. I think it makes them decently intuitive, right? The laws and why you have to follow them to be a category. Yeah. And then when we're talking about manifolds and I don't know, how do we say this word? The cobordisms?
I might emphasize the first syllable, cobordism. I don't know.
Cobordism? Okay. But yeah, so when we're looking at that, I did a little bit of reading on that, and yeah, I'm still not totally sure what they mean, but I guess I sort of realized that what was it? One-dimensional cobordism is sort of like anything that you can draw on a flat sheet of paper. So if you think of just like slicing off the very thinnest section of the top of these, you know, you can fully represent them. So they're one-dimensional, even though they're circles, which I hadn't really heard of circles being called one-dimensional objects before. But when you're talking about topology in this way, I guess they are. Yeah.
Each of the circles is one-dimensional. It's in a, you know, right? It's
both of the circles together is one-dimensional.
Well, okay, but they're like two line segments that you've, like a line segment is one-dimensional, right?
Sure.
Now curve it around so it touches at the points.
Oh,
now you've got it. Yeah.
That makes sense.
And the little top of an egg there is an arrow going from a point to a circle. It's a transformation going from a point to a circle.
Mm. Sure.
Wouldn't it be from the empty cobordism?
Could be.
From the.
If
Is
a
it
point
from
is
the-
an empty, that makes sense.
I think the empty manifold would be an object, so that would be a morphism from the empty to the. Because they use as a monoidal product, they use the disjunct union. So you would expect the unit to be the empty manifold.
That makes sense.
Oh, as opposed to 1 point. Okay. Yeah, I'd have to look at that, but that makes sense.
Yeah, I'm not sure either.
Real analysis says there is 1 point at the top, but who knows what kind of space there.
Yeah, it's interesting, right? Because like, also we're not necessarily talking about this is the point at the top, right? If we're talking about the transformation from X to Y, we're talking about the transformation from this one circle to these two circles.
Oh, really? Yeah, I guess so.
Yeah.
Okay.
And there's like a couple different ways to do that, right? So we can do it this way, or we can do it where this one circle ends up connecting to both of these two circles.
Okay, yeah, I was off in my understanding. Thanks.
Yeah. And there's Tang as well, which is kind of cool. I was confused by this note. Note that we can think of a morphism in Tang K as a one-dimensional cobordism embedded in the k-dimensional cube. This is why Tang N and NCOB behave similarly in some respects. Did that make more sense to anyone else? I guess like my specific question that I think would help guide my understanding is if, I guess part of the reason I'm confused is because they go from, yeah, well, they're just showing Tang in different dimensions here. But if anyone had an idea of what that looked like graphically, yeah, that'd be great.
So you might
basically, sure.
go ahead.
So basically, it's n-1 dimensional. So that would the objects. So that would mean they would be 0 dimensional. So basically, points are 0 dimensional, right? So then the cobordism embedded in this k-dimensional space is just like a line from one point to another point. Does that make sense?
Yeah.
In that case, I found that the actual text definition made it into my head. I think it might be up a little bit. I mean, previous a little bit. Right, that very roughly speaking.
Mm-hmm. Okay. Okay. Yeah, that does make more sense to me. Okay. Yeah, then we hit functors and natural transformations. Anyone have any thoughts or on those sections?
Just that they're only slowly going into my head.
Yeah.
They leak out very quickly.
Yeah, I find myself going and looking at the Idris definition of functors and natural transformations
Right.
whenever I have to know the details. Yeah, I didn't understand, I don't know much about groups or whatever, so I didn't understand the intertwining operator from one representation to another. Yeah, that example was lost on me. I don't know if anyone had a better understanding of that part.
Group is one of the things that stuck with me in college. I think I might be able to recite the group axioms, but this was one of those things where I like Hilbert space. I have a vague notion of what that is. Group, I know what that is. Okay, words that I kind of know. All right, keep going.
Sure.
I think a representation is a continuous action of the group on the Hilbert space, which doesn't make sense because G is not topological. So I guess it's just an action on the Hilbert space with a specific name because it's on a Hilbert space and not on any set.
Okay.
Intertwining operator.
All right.
So,
Yeah. Okay. Yeah, that makes a bit more sense.
So basically, I read the 7 Sketches book by Fong and Spivak, and they have a lot of examples. And yeah, so one explanation, which is very close to my intuition, I'm a software developer, is databases basically. And so the main idea is that you can have a category which is kind of like kind of a database schema, and from the schema to set. So set is a category of sets. So what this functor does is basically it kind of selects all the entries of the database. So this functor then basically is an instance of the database. So and this what you see here is kind of a very similar idea. You have the group, and then you have a representation of the group in the Hilbert space.
Oh, okay.
Yeah, and then if you have like 2 different functors like this f and f prime, then you can just have natural transformation between the 2 functors. Like in the database example, the natural transformation would be like a database transformation. And yeah, so going here to the group representation, it's kind of this is what I think about the intertwining operator.
Cool. Yeah, and then this is just saying like it doesn't matter if you do the database transformation sort of like first or second.
Mm-hmm. Right.
Okay.
Yeah, so the
And then we got.
I think the group presentation is also very interesting. So normally you see like the monoid represented as a category. So basically it's just a category with one object. And the morphisms in this category are basically yeah, the functions of the monoid. So like if you have a clock, like modulo 12, then you have +1, +2, and so on. And like these are the morphisms in the group. And I think this is a pretty yeah, central concept.
Yeah. Which is different than a monoidal category, right?
Right.
Mm-hmm.
It's just that you can think of categories as a generalization of monoids. Instead, like a monoid is just a category with a single point because the law on the composition of the arrows are exactly the monoidal law. And you can think of categories as a generalized monoid where like you have additional restriction on the composition of objects.
Mm.
But I think there are at least 5 concepts where you can think categories as a generalize of that concept. So depends on what intuition you're trying to get across.
Yeah. That is cool. Yeah, I hadn't heard of that generalization before. Thanks. Okay, So monoidal categories. I think this stuff makes sense.
Yeah, this is, but you have to get this not confused with category as a generalization of monoid, because I mean, they have somewhat similar structures, but they're like different parts of my brain anyway.
Yeah.
Yeah, this is saying you can pair things together, and there's a way to, there's also another structure that says that they're associative. The tensor product is associative. That's not in the Cartesian project. It's down here.
Yep. Category, tensor product, unit object. Sorry, let me close my windows here.
That was wild. The pentagon equation. I'd seen lots of things with squares or sometimes, but 5. This is the first time I've seen 5 in math. So it's all over in nature, but
yeah. Yeah, I'm not very excited to prove stuff with the pentagon equations in Idris. That's going to be a day. Yeah.
It's from what I've read is that there was a nice proof that if you've got the pentagon equation and the previous equation, like you can parentheses however you want. So people just give the pentagon equation in the definition because it's the simplest one in like from a mathematical point of view. But it does, if you don't know why they choose that equation, it just like you just look at it and you're like, why is that one specifically?
yeah.
Yeah, it's like once you have the pentagon equation, you have the ones for every single parentheses for the cross products. Yeah, that's neat. Okay. Yeah, monoidal categories being things done in parallel in series. This kind of tripped me up for a little bit, and I want to just check my understanding, which is that you have to have at least one X and at least one Y, which is why they start with Y1 and X1. And yeah, these can be of any size, the N and the M, but like underneath the hood, if, Y is smaller, it probably looks something like this, right? It's a tensor product with something else.
They can be empty. Usually you consider that the empty product is the unit of the, like you need something, but the unit is the empty product. So if n was 0, it will mean that you've got f from the unit of the monoidal product.
Right.
Okay. Got it. But wait, this isn't true generally yet until we get to, okay, yeah, okay, yep, this is where it is here with the unit.
Yeah.
Yeah, that makes sense. But we can't delete yet, right? It's only once we get to a category that has finite products that we can delete something. Right, so Y has to be full, or Y can't be empty. Is that right?
I guess it could, but you need a morphism in your categories that goes from the first object to the second. So if you've got an object to the unit, morphism from one object to the unit, it means you can delete that object.
Right, but you're not yet guaranteed to have it in just a monoidal category.
Right.
In general, yeah, okay. It's like deformation, string diagrams. It corresponds to sliding things across them. Yeah, has anyone dived further into the rules governing string diagrams and how you can morph them around and depending on what category you're in? It sounds kind of fun, but I haven't done it.
Not myself.
Me neither.
Okay, I think, yeah, past, looking at my notes here, we passed another question that I had, which I think might be a good question to ask in the chat to the authors of the paper. Where was this? There was somewhere where they said that the best behaved tangles are framed and oriented mathematically. Does anyone have an idea of, yeah, it's right here. Mathematically, the best behaved tangles are both framed and oriented. And I guess there's a couple of references there, which I should probably check out first, but I was wondering if anyone had an idea of why that would be the case. Sorry to jump back a little bit.
No idea whatsoever.
All right. Okay, then we got to terminal objects, finite products, corresponding to deletion, and some other fun things that you can do.
Go back to delete again. I want to make sure that I'm not like zoning out. Why is it that we can delete once we have finite products?
So finite products ensures that you have binary products at the terminal object.
Right, okay.
And so the terminal object aspect of that is what allows you, because the terminal object has one unique morphism going into it from all other objects.
Right. Okay, thanks.
And then did we say we were going through 2.4 or up to 2.4? I don't remember.
Inclusive of 2.4.
Inclusive of 2.4, okay. Okay, so then we're introducing a braiding, which allows you to cross these things over and have those crosses be different, right?
Yeah.
So X cross Y can be different than...
But they're inverses, yeah. So is this the proof 21? Oh yeah, so page 22 was the first string diagram where it wasn't immediately obvious to me just from the string diagram what the proof looked like. Because if you're thinking about transforming these two between each other with the Y string, I don't think you're necessarily sure where it lies, if it's like in between these two, X and Z, or is that obvious? It appealed to my intuitions that I was going to be able to use the definition of braid to make the straightforward proof, but I don't know. I just feel a lot better because there's been a lot of times where they present diagrams as if they represent mathematical equations. I'm like, what the heck are you talking about? Now at least I have some clue.
Mm-hmm.
I mean, that might be
Yeah.
an interesting place to switch over to Idris, is to take this and represent it as a formula.
Yeah, I think that's a good idea. We need to do a little bit of work to get there, but yeah, I think that that's something that we should end up doing.
We could sketch it right now, though, right?
Yeah, we could. We don't have the definition of braided. But yeah, if we could, yeah.
Yeah, we could sketch it and then go back to the beginning of the Idris
Right.
stuff.
All right. Do you want to take over for some of that?
Ooh, ouch. I'm willing, but I'm afraid it'll go really, really slowly. I'm pretty swapped out.
Okay. Yeah, I'm feeling the same right now.
Okay, so maybe that's not a good idea. Well, I would like to give it a try. Let's see how slowly and painful it is.
Maybe, yeah, I guess that kind of does, the end of this section, right, brings us through what we had planned to read. So, yeah, if there's any questions before we switch over to that, or while we're switching over to that.
So if I were going to find it, I would, your Jake Gilbert all spelled out in GitHub.
Yeah.
Oops.
What are you trying to find?
Your Idris work, your recent Idris work?
Oh, I mean, I don't think that will help us here.
Okay. I just want to look for idris-ct.
Yeah, I think just idris-ct. That's, yeah, the state box idris-ct library.
Okay, so I will make sure my copy of that is current.
Yeah, I get, so Dan and I have done some playing in Idris already. Are other people familiar with what it is and dependent types and stuff, or do we want to give like a quick high-level overview, or what questions do you have going into that?
Let's see, what's the front side of one-page version of this?
Probably just looking at basic.category. And scrolling down at the bottom.
Do they have these typeset somewhere?
They do. Don't remember exactly where right now.
Hold on just a sec.
Oh, idris-ct dot.
I guess it looks pretty good on GitHub there. Ah. So if anybody's done Haskell, Idris is syntactically a lot like Haskell. I think they changed colon and double colon around or something. But the interesting thing is that in Haskell, there's sort of data and types, and the worlds don't meet unless you're using some extension that I don't know about or whatever. But in Idris, data and types all live in the same world. So they're just saying, within a category, object is a type, morphism goes from object to type, and then compose takes 3 objects, a morphism F from the first 2, a morphism G from the second 2, and gives you a morphism from first to the third. So there's the identity law, right identity, associative identity. At this point, I'm sort of speeding up. Anyway, you get the idea. There's some diagrams and there's some code next to it, which makes me happy, or makes my brain kind of go, oh, this kind of stuff, I know how to do that. This kind of stuff. Now, if you tell me how they relate, now I can get along.
Yeah, and then with the cool idea being that if you can instantiate this type, you're sort of guaranteed to have a category that satisfies all these laws and have a like mathematically sound category.
Right, Curry-Howard in practice. Programs
as long as all your functions are total.
Oh, yeah. And it does have a totality checker that helps a lot, but it's not perfect because Gödel's theorem. So there's the whole definition.
It is perfect in the sense that if you've proved that your function is total, it is total.
Yeah. Just the other way around. You can have total functions that it can't figure out. So that's fun with idris-ct, or that's a brief intro. And then if I switch to, did I not have it open already? Okay, so if we wanted to look at something like product, I'm just swapping myself in here partly.
Products is kind of interesting because there's a product category, and then there's also, if you go into limits product, that's kind of the idea of a product that exists inside of a category. But then that's really defined in terms of a coproduct. So you might want to go into the colimits coproduct file.
Into the what?
The source colimits coproduct.
Come on.
Because of, yeah.
I messed up a tendon in my finger the other day a little bit. Typing's just a little bit different. So when they say record, they're making a record type?
Yeah, they're making...
Record ends up being shorthand for something, I think. It's not novel.
Yeah, it ends up being data type, but it has, it just like automatically has like accessor functions and stuff for you.
In other words, the sort of proving as a game theory goes, if you can get through all the steps in the adventure game down here under where, then you get the prize coproduct.
Yeah.
And this is exists. Okay, so now I'm starting to remember the syntax. If I wanted to do braid. Oh, part of the Emacs is remembered what Idris is.
So Eduardo has a question, maybe So he's asking or believe me if it can be used everywhere. So this is a function which occurs in the source code at a lot of places.
Oh, yeah. If somebody either got tired of making up the proofs or whatever, yeah, there's a thing where you can just say "believe me," and the Idris compiler will go, "Okay." You're saying that's used a lot?
I haven't seen a look through the code, but yeah, it pops up in some places. Looks like that. Yeah.
Yeah, it's true. It is kind of a hole. Yeah.
Unsafe in Rust. How do you spell it? Is it believe_me or something? Yeah. Oh, really believe me. It's only 3 times. Hey,
Really believe me. Yeah.
I give him a B+.
But then they also are using proposition, which is similar.
Oh, really?
So, yeah, for type extensionality or functions extensionality. If you look at types as function extensional, so idris dev source idris.
Where do I go from here?
Idris, and then types as function and types as category extensional. Nope, not that one. Extensional. Yep. And then if you search fun.ext, so that's similar, right?
Postulate. I didn't hear what you said earlier.
Yeah,
Okay.
I think I used the wrong term for it. But
Okay.
that's similar. That's like, here's a property that we're not proving because it can't be proved in our type system, but we'll use everywhere in our code.
So you're sort of adding an axiom to Idris in a way.
Yeah. Mm-hmm.
And that can't be proved, or they just didn't want to?
Well, yeah, I think there's some definition somewhere about function extensionality in Idris, but yeah,
Yeah, I'm pretty sure functional extensionality cannot be proved in Idris. It cannot be proved in Coq. Like, it's something that is independent from the usual type theory axioms.
yeah.
Wow, learn something new every day.
Yeah, if you look up function extensionality, I think there's an account of it somewhere.
In idris-ct or in?
No, in Idris. I think like Edwin Brady maybe has a reason why it's not included. Maybe not. I can't find it now.
Okay.
So.
We're definitely off the reservation as far as my knowledge of stuff.
Yeah.
So
you wanted to just like jump right into making braided categories. I thought we were going to start from, say we have a type called braided monoidal categories. What would the statement that these two things are equal look like?
Either one, yeah, that would be fine too.
Yeah. I think that's probably the place to go.
Okay. Zoom does funny I can move it over there. Your screen sharing is now paused. That's not what I wanted to do. I just want that thing out of my way. Okay. Am I back? No, it's paused. Resume share. Okay.
Up a page. Right there.
Man, I can't remember anything. How do you say, is it data type or type? Is it data type or type? Wow. Echo.
Yeah, it's data.
Okay.
If you look at the definition of monoidal category or symmetric monoidal category, you might be able to do something.
Where do I see symmetric? Ah, it's doing it again. The Zoom thing gets in the way. Symmetric doesn't occur. What am I doing wrong? Oh, I'm looking at page.
Probably just not in the, yeah. Also, like these things don't really have nice explanations for them. I guess you can.
Well, I'm going to peek at some code that I wrote. Maybe I can remember my own. Hold on. Oh, well. Where's there? Just get my head reoriented just a little bit. Oh, right. So this was was my intro to Idris class. intro to functional programming in a way. I sort of spontaneously gave one Saturday morning. Okay. All right. We'll just assume somebody gave us a braided, right?
Sure. We'll have to know a little bit more what's in it, but yeah.
And it's how many things do we talk about when it's braided?
So
I guess it's the category that's braided.
Yep. And it's the monoidal category that's braided.
Well, right. That, you know, where something like that. I don't know.
That assigns to every pair of objects in isomorphism.
That would be an obligation for figuring out something is that, and it looks like there's when you talk about a braid, you're talking about a category and a braiding, right? There might be some category that's got two different braidings.
Yeah.
Yeah. Okay. Okay. So I'm going to assume the rest of that definition for now. Is that fair?
Sure.
Yeah, I guess technically you would need a proposition about the braiding being correct, but
Really, there's no way we could state the type, state the property.
So here, let me pull up something.
to state the property should be all right. To prove it, you would need it, but to state it, you just need the braiding.
Yeah, well, the type is just the theorem, right? The type is not a proof.
Yeah, but if you want to take like a braided category as argument, you would like that the braiding operator is actually a braiding operator.
Oh, sure. Just like it's ismono, yeah, is braiding.
Yeah, something like that.
But the other thing is that this is the definition. This is where we would put what braiding means. So I don't think I would have a separate is braiding. It would be something like, you know, for all.
Yeah, exactly.
I would have to spell out the hexagon equation. Which I would need a quiet room in 6 hours to do. Actually, okay, I have fumbled around long enough, I think. Jake, do you want to show us any of this that you've actually managed to do?
Sure.
It's getting late here, so I gotta go. See you
Oh,
all
right.
next time.
We're just about at time.
Well, thanks for coming.
Bye.
Yeah, so the first thing that I started in on was trying to make the data type of Cartesian category, because that was sort of the first thing in sequence of the paper that didn't have a definition in idris-ct.
Okay.
So yeah, I guess my motivation here was to have this data type data Cartesian category where it contains inside of it a monoidal category. It has this tensor object, and this tensor object corresponds exactly to the monoidal category tensor.
Okay.
I guess the tensor is a functor, so that was kind of weird. So I'll get to that later. But I guess if you look at these two lines, the unit is a terminal object, and so I have this terminal object unit, and if I specify the carrier of that unit, that gives me the actual object in the category, and I'm saying that that must be equal to the unit object in our definition of monoidal category that exists up here.
Wait, the carrier thing, say that again?
So carrier unit, so a terminal object, so a terminal object is an object in a category along with some properties.
Oh, okay.
Right. So to say that, and in a monoidal category, the unit is just a specified object.
Okay.
Right. That doesn't necessarily have, it does have some properties to it, but they don't correspond exactly to the terminal object properties.
Right. So you're sort of picking some gunk out of unit when you say carrier. Or
Yes.
You're picking the object out of it, right?
Yep. So I'm saying that essentially, if we have a Cartesian category, we can ask for the unit object in one of two ways. We can get the unit object that like exists as the terminal object of the category, and we can get the unit object as it exists as the unit of the monoidal category and satisfies the monoidal category laws.
Right. And this is commented out because something's not working?
No, it works fine. It just takes forever to compile.
Right, okay. Oh, did you try Idris too?
I should, but yeah, that looks like there's some big issues there too. So anyways, so then the other thing that I had to do the similar thing for tensor, which meant that I created this binary product type, which I can show you. And then I essentially had to prove that the tensor object of the monoidal category, which is the functor, is the same as this binary product. So I needed a way to like translate binary products to functors,
right,
and then claim the equivalence. So with that sort of motivation in mind, we can go up to, I guess the next logical place to start is probably at binary product, right?
Can I, we are at the scheduled time, so we can go longer, but we should talk about it, and we should talk about it the next time.
Sounds good. Yeah, I'm okay going like 15, 20 minutes longer. And in terms of the next time, I think we should probably, the closed category section is pretty big.
Yeah, that's kind of a level bender. I started reading that.
Yeah. So maybe, yeah, Dagger categories are big too. So I don't know, do we just want to try to get through closed categories and implement a bunch of stuff in Idris from the previous section? Because we have plenty to
That's
implement.
That's interesting to me. Can we hear from anybody else? I wonder if, what's his name here? The guy who's not here with us today, quantifier, Chris, what's his name? Anyway.
Oh, yeah.
Wonder if,
Isaac.
if he's going to want to join next time.
Yeah.
Because if so, we could do a certain amount of catching up, but I forget who was here. So Tomislav or Johannes, are you likely to join if we do this again?
Yeah, so we had like this on page 22. There were these two equalities. They where you said that that they are not obvious. Yeah, these two. Maybe trying to prove these. So yeah, we could try this. I think we have two. I think the question is, do we want to proceed in the paper and like go through the paper, or do we want to focus more in Idris? I'm fine with both of them, those options.
Yeah, we should kick the idea around, because the way I can read a paper and that's fine, but it doesn't stick until I translate it into Idris for myself. And watching Jake do it is somewhere in between. It's like I can understand it a little better, but I have to sort of do it myself in order for it to stick in my head. But I don't know. Right, we could also just talk through more of the paper, but I think my understanding would get more and more thin as we go.
Yeah, it seems to me like go ahead.
So I think we talked about a lot of stuff, actually. I think going like to categories and functors and natural transformations is already a huge amount of information, basically. And yeah, I think if we go like through the rest with this speed, maybe we could miss some details in the end. So
the natural transformation, is that stuff you are reading for the first time in this paper, or have you had classes on that? Or
yeah, I had classes. So yeah, I read the Mijewski like categories for programmers and 7 sketches, and it's treated there in extension. Yeah.
right. I mean, it's like I said, I don't know that stuff by the back of my hand, but that's not the meat of this paper, right? This paper kind of, glosses over that somewhat briefly. Although, I mean, if you go back to that tree diagram, Jake, I'm getting the sense that the meat of the paper is about the difference between set, which is Cartesian, and all these interesting things which are not Cartesian.
Mm-hmm.
Yeah. Yeah, which is why I think it would be really nice for me to, further see the differences, to have Cartesian categories and braided monodal categories implemented.
I think just doing one section makes a lot of sense given how big the section is.
Yeah.
And I think if we don't get up through all the way through it, that's okay too.
Sure.
We'll see how it goes next time. Tomislav, I haven't heard from you at all.
Yeah, I'm just following, and yeah, I will join definitely next time.
Okay. And the logistics, should we just leave it like it is? Because it's really hard if we change it.
I think that's fine.
Okay. So at this point, we should probably just say anybody who wants to stay can stay, and anybody who isn't, it's late or whatever, we'll
Sure.
go on for a little bit longer.
And as this code is all really messy right now. As I start to firm it up and put it into like a work in progress pull request, I will, I'll post it.
Oh, are you actually doing a pull request to idris-ct?
Yep.
Oh, cool. I hadn't thought of it that way for some reason.
Yeah, I've had a couple things accepted by them. So, and this is actually proving that Idris is a Cartesian category is an issue that they have open. So,
Oh, cool.
Yeah.
Have you looked into what they're doing otherwise, Statebox?
not a whole lot.
Okay.
I know that, like, yeah, not a whole lot.
Neither have I.
There's some good discussions. A couple of the Statebox people are on the Zulip chat, so it's fun kind of reading some of their things. So where we left off was defining a binary product.
Mm-hmm.
Hello.
Hello.
And
Wait, is that Henry's story? Seriously?
oh, I think you're muted.
Who's speaking?
Oh, I know somebody named Henry Story. I wonder if it's the same person.
Is it Dan? Is it Dan?
Yes.
Henley? Yeah, that's me.
Holy moly!
Is this about the Rosetta Stone?
Yes.
I'm late, aren't I?
Yeah, we meant it. We ended up scheduling it an hour earlier.
Oh yeah, no, I was doing something else. Yes, is that he's talking about the famous article Rosetta Stone?
Yes. Well, it's archived by Stay and Company. I don't know how famous it is or whatever.
It's pretty cool, but we're looking at code, all right? I'm just trying to follow along. I
Yeah. So there's two of us at least here who understand papers much better once we can translate them into Idris.
Ah, right, cool, all right, interesting.
Yep. And then there's a library that's trying to translate a bunch of category theory stuff to Idris. So we're hoping to sort of wrap up some of the definitions in this paper and submit them to that library. Yeah. So yeah, once we have binary products defined, which is just this idea that for any two objects in a category, we can form a coproduct, or we can do the same in the dual category. That have you seen this section, Dan? How like in the idris-ct library they define a bunch of the limit stuff as co-limits?
No.
Okay, so yeah, they have this notion of a dual category, which is the category where all the morphisms are flipped.
Oh, okay.
So a binary product is just a binary coproduct in the dual category.
Okay. All right.
Yeah.
But wait a minute, isn't that sort of reduction the previously unsolved problem? What's a binary coproduct in the?
Well, but then binary coproduct is then, so in this library, they sort of do all the definitions on the coproduct side, and then on the product side, they refer to the coproduct definitions.
Any idea why?
No.
Okay.
I mean, I guess it's like, it makes things more compact to do things in one space than the other, or to not replicate code in both spaces, I guess.
Well, sure.
But I don't know why they chose to do it on the co-limit side as opposed to the limit side.
Okay.
So then once we have that, we have to, where we left off is we had to get a binary product into a functor.
Okay. Yeah.
So here is some ugly code here that's not yet complete. It has a hole for preserving composition. But you know, we essentially have this product, or that for this idea that for any two objects in our category, we can form the find the product object of them.
Right.
And then using that to prove sort of all of the functor laws.
Okay.
Where
Oh, okay.
we're an object in the product category, so we're sending the objects that are of the form pair AB to the carrier object of this product of A and B that we have.
Is it straightforward to look at carrier?
Yeah. So we have to pull up coproducts for that.
Has this been recorded so I can
Yeah.
catch up?
Yeah, it is recorded.
Oh, great.
So a coproduct is in a category, and two objects in that category. We have this carrier object, which actually like is the coproduct object, and then all these we have a morphism from our left object to that carrier. We have a morphism from our right object to that carrier. And then if you think of this as a product is just a coproduct in the dual category, our INL that we're looking at for our product is a morphism from our carrier object to the left object.
I'm going a little slowly here. Where did obj get into scope? I guess it was sort of implicit in the before the where.
So this is the record thing where object is a function that takes a category and gives you the object type of that category. So that's going all the way back to the definition of category.
Oh, okay. I'm a little slow. Thank you.
That's fine. Yeah. So obj_cat is just the type of objects in our category, and then more_cat is the morphism in our category, and this is our category here. So the more is coming from that, and then it's a morphism from our left object to our carrier.
So this gives you the coproduct of any two objects in the thing. It's not like saying, okay, right. It's coproduct on a sort of pair by pair basis.
Yeah, this is the coproduct in a category. So you'll have multiple of these records coproducts in a category.
Right, just make up
that has products.
Okay.
Yeah.
We were looking at some occurrence of carrier. There it is. Okay.
Yeah. Was it this one? Yeah.
Yeah.
Okay, so this is like a pattern match deconstruction of our pair. Yeah. Of this, which is the object. So the object in the product category of the category with itself is a pair of objects.
Right.
In that category.
Well, in a different category. Oh, if it's it's got products, and it's the same one. This makes my head hurt.
Yeah. I mean, this is really annoying. It's like very tautological looking because we're just, saying that that a binary products can be thought of as a functor in a category.
Right.
So yeah, it might not be that interesting to look over this code, but there still is more to do, right? So the objects go here.
No, but this is really useful for me swapping in. Just remembering how to orient my brain this way.
Yeah. So preserve ID is done. Preserve composition is not done for that, for proving that's a functor, for this binary product of functor. So yeah, I just kind of got bored and wanted to move on.
Sure. How many hours are we looking at here?
Maybe 4. Oh wait, how many hours to complete all this stuff?
Yeah, to write this code.
I don't know. Total.
Have you been working on it since before this week? I guess.
No, I guess I've been working on, I did things like I proved pair was a product in Idris. That the data type pair was a product in the category of Idris. And a couple of other things, but and all this stuff sort of is related, but yeah, none of these lines of code were written before this week.
But you've been in idris-ct for a little while now.
Yeah.
Yeah, I looked at it and went, wow, that's really cool. That really helps with me understanding category. And then I went, oh, shiny thing over here, and looked at something else.
Yeah. Yeah, my main motivation initially getting started on this stuff was taking the MIT course programming with categories, and then having to do the homework problems where solutions weren't posted and they weren't being graded for me, who was just an observer.
Right.
And I wanted to make sure that my proofs were
Right.
good. This is the way that I know how to do that. Okay. So yeah, the definition of Cartesian category, then I think we've gone through that. And then I don't know that I really love this definition of Cartesian category. I think that it might make sense to just have Cartesian category like this be a function from finite products to a monoidal category.
Oh.
Because up here, right, we're not actually proving this stuff. We're just like giving these as propositions and leaving them up to be a proof for later. So
right.
I'm sort of interested in this method of doing it, which is, I guess, another reason why this is commented out, because I don't think that data type's actually really that useful.
So we believe this is a theorem for the first, to start with. Every finite product category has a monoidal, there's a monoidal category too?
Yeah, that comes from it. That's in the paper. I don't remember what page that was on, but.
Okay, so lots of people believe that's a theorem.
Yeah.
And does your proof type check? I mean, you got that to work? Oh, you got lots of question marks. Okay.
Yeah, basically I haven't done any part of the proof yet. So these are all the laws, these are all the equations, the equality types that that are left to do.
Right.
These are just saying that there's a monoidal category that's the same category as the category that has the finite products. And there is, I guess, so I've done part of it, right? Because I've done this binary product to functor.
Oh, right.
Part of it. So yeah, if you take, and then the terminal object is the carrier. Yeah, because finite product is just defined as something that has binary products and a terminal object. Yeah, so if anyone, I guess I can post this link again. This is just like the really messy version. Yeah, it's just sort of in there with all my other Idris hacking if people are interested. But I'm hoping to clean it up and post stuff. I'm just having idris-ct takes forever to compile, so it's kind of difficult to work with, especially when you like to do the interactive.
Oh yeah. That Idris is much nicer if you can do interactive stuff.
Yeah.
Are you on a Linux box?
Yep.
What happens if you type snap?
Type what?
Snap, S-N-A-P, and enter. Does your box have snap on it?
No.
Oh, okay. It's a Ubuntu thing. It was just, I was looking at the options for installing Idris 2, and it said, try snap install Idris 2. And I went, snap install Idris 2. And it said, here's Idris 2. I went, wow, that was easy. You know, given how bleeding edge it is.
Nice. Yeah, I do all my development inside separate Docker containers too, because I'm weird. They're all Debian things.
Right. I don't think that's weird. We all have to do something that everybody does something like that,
Yeah.
unless they only have to work on one project.
All right. Yeah.
Okay, doing this again in the next week. Well, I think it's good that at least some people do it. I'm sort of more at risk this week than last, but crossing my fingers.
Okay. Sounds
Thanks a lot,
good.
Jake.
Yeah, thank you. Nice meeting everyone. See ya.
Guys.
Good seeing your
Thanks.
face, Thomas.
Bye-bye.
Bye bye.
Hello.